Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to go over an exercise where we're going to find the center of mass of a planar lamina. And planar laminas are sort of like three-dimensional objects, and in this problem they all come with uniform density. The problem here is that we have different planar laminas with different geometry, and the geometry is governed by the given curves. And we have three sub-questions here, so you'll have three different regions to work with. But at this moment, I want to remind you the formulas for finding the center of mass of a planar lamina, because we have to rely on to integration. So this is not finding the center of mass of a two-dimensional system. So this is a completely different deal. We have to rely on to integration here. So what do we have? Let's just quickly go through this. We have two functions f and g, continuous functions f and g, such that f is strictly greater than or equal to g, which essentially means that the graph of f is always about the graph of g. And we're given the interval AB. And also we have uniform density, obviously. So, and just imagine the region bounded by the graphs of f and g, and x is stuck in between a and b. So you can find two things. Well, moment about x-axis, moment about y-axis. Okay, so these are two formulas that we're going to use along the way. In fact, these two are needed in writing the coordinates of the center of mass here, which is given in terms of x bar and y bar. So x bar is m sub y divided by capital M, lowercase m, and y bar is capital M sub x divided by little m. Okay, and m here refers to the total mass of the lamina, which is also found by an integral, f minus g integrated multiplied by rho. In fact, that integral corresponds to the area of the lamina, but if you multiply it by the density, so in fact you get the mass of the lamina. All right, so before we get started, I want to give you some heads up quickly. And in the first problem, you're going to have a planar lamina coming with this type of region bounded by a blue curve, x-axis, and a vertical line. And in the second case, the region looks like this. I can immediately say that the center of mass, which is the red dot, is located on the y-axis because the geometry has a symmetry about the y-axis. And in the last one, you're talking about a curve and a line and the area in between these two, as you see. And the functions, by the way, are provided in terms of y. So we're going to sort of like try to, at least for this problem, we're going to try to modify the given formula written in terms of y. So all of the integrals are being converted to y versions of those. All right, so this is going to be a long video. I'm going to split it into 3 videos. And let's buckle up and get started. All right, let's start with part A. We have y equals 1 over 3x squared. We have y equals 0, which is in fact the x-axis, okay? And we have the vertical line x equals 2. And what we're going to do here is to find the moment about x-axis, the moment about y-axis, and finally we're going to find the center of mass for the lamina bounded by the graphs of these 3 equations in part A. Okay, so first of all, why don't you have your graphing calculator ready and try graphing y equals 1 over 3x squared from 0 to 2 and see what you're going to get. And in the meantime, I'm going to show you what I got here. Okay, so this is a lamina, and this is the region being told about, the yellow part, and we're going to try to locate that red dot over there, which is the center of mass. Okay, so and then this is a homogeneous density planar lamina. So the center of mass should be somewhere close to here. Okay, so we're going to again determine the center of mass of the lamina. All right, so let me just take you back to the formulation for this problem. Essentially, the formula goes like this. If you have two continuous functions f and g such that f is greater than or equal to g, so in terms of their graphs, f is always at the top and g is always at the bottom. And we consider the planar lamina of the uniform density rho bounded by f and g, and x's are stuck in between a and b. So then we can talk about the moments about x and y axes, okay? So we're going to use this formula and this formula all the way. So we're going to take the average of f and g multiplied by the difference f minus g here and integrate. And obviously we multiply by rho. And for m sub y, we're going to multiply x by the difference between f and g, and we're going to integrate. And the center of mass is the moments divided by m. So x bar is going to be the moment about y-axis divided by the m. M is the total mass, by the way. And y bar is the moment about x-axis divided by the total mass. And the total mass also has a formula coming written in terms of an integral of f minus g multiplied by rho, integrated from a to b. Okay, so we're going to have a lot of integral calculations here, and I'm going to copy those formulas down to my next slide, and let's see what we can sort of like label our functions as like f and g, and then we can come up with x bar and y bar. All right, so I listed the formulas here, so we're going to label f and g here. If you compare these two functions, so let's say like f of x equals 1 over 3 x squared, and g of x equals 0. Obviously, f is always greater than or equal to g, and in fact, in the region, as you see that the blue curve is in fact f of x, and the x-axis serves the role of g of x. Okay. So as you see that f of x is always greater than equal to g of x. So I can go ahead and plug in 1/3 x squared for f and 0 for g in the description of capital M sub x, capital M sub y, and a little m. So why don't we do that, and we're going to take care of the integrals next, okay? So m sub x is going to be rho, integral from, oh, by the way, a and b are going to be 0 and 2 because the region here is in between x equals 0 and x equals 2. Okay, so let's go back to the formulation. So we have 0 to 2, f plus g divided by 2, so that's 1/6 x squared, and f minus g is 1/3 x squared. Okay, dx. Okay. All right, so we're going to write m sub y now. That's rho times integral from 0 to 2, x times 1 over 3 x squared. By the way, rho is not provided us as a number, so this would work, in fact, any planar lamina with any density, right? So once you know the density of this lamina here, the yellow region, then just plug that in and then find moments about x and y axis. But for the calculation of x bar and y bar, we won't need that, and I'll tell you why. Okay, so let me just write down a little m. Rho times integral from 0 to 2, f minus g dx. Okay, so I think we're done with all substitutions here. So I'm gonna erase this part because I don't need that anymore, and I'm gonna move the bottom formulas up here. Okay, so let me just do that real quick. There we go. Okay, so because I need space for the calculations of integrals, so here we go. I have 1 over 18 x to the 4th inside the integral. So rho, again, this is 1 over 18 x to the 4th. So 1 over 18 x to the 5th divided by 5 is the antiderivative of that. So essentially this is x to the 5th divided by 90. from 0 to 2. Okay. And this takes you to, let's see if we have any simplifications here. Let me just double check everything. So that takes you to 16 divided by 45 rho. Okay, here we go. 2 to the 5 is 2 to the 5th is 32. 32 divided by 90 is 16 over 45 rho. Okay. All right. For this one, we have 1/3 x cubed. So this should be 1/3 x to the 4th divided by 4. So in total, this is x to the 4th divided by 12. Okay, x to the 4th divided by 12 from 0 to 2. Okay, so 2 to the 4th is 16. 16 divided by 12, that's 4 rho over 3. And 0 doesn't have any contribution here either. Okay, so is here, right? So this 0 here does not have any contribution for the final output. And finally, what do we have here? So we have 1/3 x squared, so 1/3 x cubed over 3. So that makes it x cubed over 9. Okay, x cubed over 9. Rho from 0 to 2. Okay. And 2 cubed is 8. 8 over 9 rho. So 8 rho over 9. And 0 doesn't have any contribution here. Okay. Let me just go back to my comment about the location of the center of mass. That is supposed to be independent of rho, because at the end of the day, I'm going to divide m sub y by m, and those rho's are going to be canceled out. And same as for m sub x divided by little m. So we're going to cancel all the rho's. So in other words, let me just continue from here. So x bar is going to be m sub y, so 4 rho over 3 divided by 8 rho over 3. Okay, and that is after you cancel the rows and flip the bottom over. So you have 4 over 8. Let's see, 8 over 3. Is this 8 over 9? I'm sorry, this is 8 over 9. Oops, let me just correct that. Okay. So then x bar is going to be 3 halves. Okay, and the y bar is going to be m sub x. So 16 rho over 45 divided by 8 rho over 9. Okay, if you simplify that, and if you cancel out the rows, you have 2 over 5. Okay, so as you see, rows always cancel out when you write down x bar and y bar. So x bar and y bar, in other words, are independent of the density of the planar lamina. And why is that so? Because if I have a lamina like this, it doesn't matter if it's made of steel or cotton or any other lighter material. At the end of the day, if the weight is distributed homogeneously, okay, so the center of mass is going to be located at x bar and y bar, which is again independent of the density. Okay, in this regard, x bar and y bar has so x bar and y bar are like 3 halves and 2 over 5. So here we go. If I want to write down the coordinates of that, so 3 halves and 2 over 5 is the location of the center of mass. So if you place a hoop here, and if you just lift this whole planar lamina up, so that should be staying flat all the way in the air. Okay, that's what center of mass means. All right, so this is already a long video. I'm going to stop right here, but we still have part B and part C. Please continue my next video to see what I'm going to do for part B. Bye.